we have in detail studied about the global dynamic techniques or the vibration techniques. So did you encounter what were the limitations of the global vibration techniques? What were the limitations we had seen existing in the global vibration techniques? If you recall
So
correctly,
generation of mode shape, we can get only first few mode shape,
yeah, exactly.
and and
Uh-huh.
later it was very difficult to get the after
Mhm.
after a larger mode shape. It is very
Absolutely.
difficult.
Absolutely. So, what we have recognized, and is also recognized by different researchers, we had covered a case study involving a real bridge which was being decommissioned. So, what they found that for small level of damage, there is hardly any change in the natural frequencies and the mode shapes, and there could be errors in our interpretation. Many of the techniques they require human judgment to pinpoint the exact or the correct damage location, because the reason is that these techniques, the global vibration techniques, they rely on the global vibration modes. So global vibration modes, their character is global in nature, so they are very less sensitive to incipient damage. So today we are covering details of electromechanical impedance technique. So this is also a vibration based technique, but then its principle is a bit different. So that makes it unique. It operates at high frequencies. The global vibration techniques, we can obtain mode shapes. So those mode shapes is such that when you will be doing the experiment, the next experiment in the coming week, you will find that it's quite tedious to obtain the mode shape. So of course, in the first instant, we'll be using the manual method, and then we'll also give you some MATLAB program to do that, but you will encounter that it's basically tedious to obtain the mode shapes, and even if you obtain, then also it needs quite of human judgment to correctly get the damage location. So I'm providing here basically the other technique, electromechanical impedance technique. So this technique is aimed to complement the global vibration techniques. So in this presentation, we'll be covering on the principle and case studies. So there will be other lectures also devoted to this technique. So today we'll restrict ourselves to principle and some case studies. We'll not touch details on the mathematics. So we have already seen that the piezo sensors which are central to this technique, they basically show direct effect and the converse effect. So direct effect means that when we are applying a dynamic stress, then that leads to the development of charges, and depending on the way the stress is acting, there will be the positive and negative electrons. So here if compression is acting, then the positive and negative will be opposite to what when the piezo patch is under tension. And then the piezo sensors, they also exhibit converse effect. So you have seen in our lab experiment also that when we were subjecting the patch to this kind of electrical excitation by an external voltage, then by its vibration and being bonded on the structure, it led to audible sound. So that was the converse effect. So these direct and converse effects, they are basically use the direct effect for sensing and the converse effect for actuation. Now the EMI technique basically uses both these direct and converse effects together. So we will just dwell upon the type of piezoelectric materials available in the market. So basically there are two types of piezo materials available in the market: ceramics and polymers. So among the ceramics, today most widely used ceramic lead zirconia titanate. So it's one of the 200 ceramics available today. There are multiple types of piezo materials available in the market, but PZT or lead zirconia titanate is the most widely used. So it has high stiffness, but then its drawback is that it's somewhat brittle in nature. And among the polymers, polyvinylidene fluoride is very popular. It's ductile, but it has less stiffness. So the PVDOS is suitable as a sensor, but it's not suitable as actuator. Now in the EMI technique, we need the piezo material. It should be good for both sensing and actuation. So that's why we use ceramics, and typically lead zirconia titanate is very good for the EMI technique. So these are some of the commercial variants. So here basically you see a number of different patches. For example, this is the one we have used in our lab. So what you see here division in the form of in a boundary, an insulating boundary. So the top electrode is there, and the bottom electrode is also wrapped around on the top surface. So when we are bonding the bottom electrode to the structure, at the top itself we are able to make all the connections or the soldering. But then there are other types of patches. For example, this circular one and this square one. This does not have this flexibility. They are like top electrode you have to bond to the top, and the bottom electrode you have to solder to the bottom. Of course, there are ways of doing that. Very thin film we have to insert below the bottom electrode, and then also we can do soldering. Okay, then we have this one. This is the very flexible type macrofiber composite, and this is CVS or concrete vibration sensor. So this is our own lab. So typically this is the size 20 mm diameter and thickness 10 mm, and here we are showing the macrofiber composite. So it's a flexible type. It is not brittle because it is made with piezo fibers. So piezo fibers are there, so that's why it can bend very easily. It does not break. Otherwise, PZT itself, the bare PZT material, is very brittle in nature. And this is composite configuration concrete vibration sensor. So here the piezo is embedded inside the concrete capsule, so it can stay inside and well protected. So this can be used for concrete structures. Okay, going further now, how does the electromechanical technique work? So here what we have to do, we have to bond the piezo sensor on the structure. But then here the sensor is playing an additional role. The piezo patch is playing an additional role of actuation also. So for actuation, what we have to do is we have to apply an external excitation. So we use LCR meter for this purpose, and we use a frequency of 30 to 400 kilohertz. So why we have chosen this high frequency? Because now in this method our target is to be able to pinpoint incipient damage. So that's why we have chosen high frequency, because high frequency means the stress waves, as we'll see in the coming slides, that is very small. So the stress waves which are propagating away from the piezo patch, they are small in magnitude, so they can very easily get affected by any incipient damage. So incipient damage means very small damage. We'll show by example. Alright. So what we do, we excite the structure by exciting our piezo patch into vibrations, and for that purpose we are applying an external excitation, a harmonic signal, which is applied in a sweep mode. Sweep mode means that we are changing the frequency of the impressed signal with time. Alright. So here we have represented the structure in the form of impedance. So we'll define this term, what is structural impedance, in the coming slides. So it's also a representation of the structure. So if we use impedance approach, then impedance approach means it's a mechanical impedance. So mechanical impedance means that the structure is seen as a combination with inherent mass, stiffness and damping. So this impedance approach will be going in detail in the coming lectures. So what we do is, as the patch starts vibrating and it also interacts with the structure. So first of all, we are making the patch excited, so that means we are using the converse effect. So converse effect means that the structure is now set into vibrations. But then because the patch is connected to the structure, so the structure also influences the patch. And as a result, because this is not a free piezo, so what will happen is that as a result of the interaction between the structure and the piezo patch, the electrical circuit, it gets indirectly the mechanical properties of the structure, they are reflected in the current flowing through the circuit. So that is now the direct effect. Because the structure is undergoing vibrations, so the stresses will be developed in the structure, and those stresses, they cause basically the accumulation of the charges and the current flows. So the current that's flowing in the circuit is a reflection of what is inherent in the structure. So what we do is that we make measurement of this current, and once we have current, our applied voltage is constant, but the current will keep on changing with the frequency. Here we are giving, say, sweep signal. We are selecting one starting frequency, and then we are also choosing an increment, and slowly we are increasing the frequency. So at the end we'll have an array of all the values of the current. But now the current and the voltage, they will not be in phase. There will always be some phase lag. For example, in the case of the mechanical vibrations also we have seen, whenever there are mechanical vibrations, there is a phase difference between the force and the displacement. So similarly here also there will be always a phase difference between the current and the applied voltage. So what we are doing is that we are finding out the admittance of the circuit. So what is admittance? Admittance is the ratio of the current to voltage. So we are used to the term electrical impedance, but here we are using, for the case of the electrical system, we are using admittance, so that we don't confuse between the impedance. For structure we are using the impedance term, and deliberately for the case of the electrical counterpart we are using the term admittance. We can do in the other way also, it's up to you. You can bring the voltage, applied voltage, in the numerator and the measured current in the denominator, so that's also possible. So in that case it will be electromechanical impedance, but we should use the term electromechanical. So this admittance is electromechanical admittance. So because it's imaginary, it has imaginary component also, so the real and the imaginary components, they can be separated out, and the real part is called as conductance and is denoted by symbol G. The imaginary part is called susceptance and is denoted by symbol B. So G and B, they are the equivalent. They are the equivalent of resistance and reactance. Otherwise, in the LCR circuit, if you just recall your plus 2, so what we do is, if LCR circuit is there, we find out the resistance, which is basically the dissipative component. So resistance is just like or damping in the structures. And then we have the other component, the reactance. So reactance is in the terms of the mechanical systems is equivalent of mass and the spring. So pure mass and pure spring, they don't consume energy. So here we will be using the inverse of electrical impedance. So that's why we have used the symbol conductance and susceptance G and B. So it's clear to everyone? So here now it's very clear, the same patch, it acts as both sensor and actuator simultaneously. So this technique was originally developed for aerospace structures, but now it has come to civil structures and mechanical structures also. So any doubt till now? If you have any doubt, just raise hand, then we go on the next part. So I hope no doubt. So basically here what we do, we acquire a sort of signature. So what we have done is that we have connected the patch to LCR meter and we are applying a sweep signal. So this sweep voltage signal, this is a sweep signal, what you find is that the frequency is constantly increasing. We may start at say 30 kilohertz and we may go up to say 130 kilohertz, or we may go higher, or we can choose any subset. So this is something to be decided based on the trial. So the outcome of this is the admittance measurements at multiple frequencies, and the data is just like an array or a one column matrix or a vector. So that forms the signature. So typically the signature looks like this. So this is the conductance part. So what you see here, this would give you an impression very similar to the frequency response function. We have just now seen we acquired the frequency response function, of course for low frequency, but this is the frequency response function for quite high frequencies. So here for example you see the range is from 140 kilohertz, so everything is in kilohertz, and it's going up to 165 kilohertz. So the peaks, what are these peaks? They are also some resonance peaks, but these peaks, they are not the global modes of vibration, they are highly local modes of vibration. All right, so now let's compare and contrast with the global vibration technique. So in global vibration technique, what we do, if we use shaker, we also apply a sweep signal. So in the EMI technique also we are applying sweep signal, right? So that way the two, they are similar, but the difference is that we are not using an exclusive shaker. In our case, the piezo patch itself is acting like a very small shaker. So it's basically acting in a horizontal fashion, and it's basically exciting the structure to undergo flexural vibrations. So it's also a vibration based technique, but it does not involve separate actuators and sensors. The piezo patch itself acts like both actuator and sensor. Then what is the measured quantity of the EMI technique? So my question is that we, in general, when we are finding out the FRF, what we need force and we need the response. So here, can you tell us what are the equivalents, force and the response here? What is force here and what is response here? I hope you are all getting on with me.
Sir, force is applied to the shakers, and the response of what we get in accelerometer.
No, I am talking about the EMI technique. So in the EMI technique, what is the shaker in the EMI technique? First of all,
Voltage and current.
yes. Who said that? Voltage and current?
So, me, Madhu.
Yes, Madhu is correct.
Hello.
Yes, correct. You are correct. So in the EMI technique, basically we are applying an external voltage. Alright, so that is the equivalent of force, because when we are applying voltage across the piezo patch, it makes the piezo patch undergo vibrations, and that sets the structure into vibrations. So that's like force. And what is the response here? So the response here is in the form of admittance. So we are not directly measuring the current, we are indirectly measuring it in terms of the admittance. So this is here the force and the response. So that's why when we are plotting admittance, so we are in fact getting FRF kind of thing. So here we don't need to specifically carry out FRF. We don't need to specially carry out fast Fourier transform here, because we are getting the FRF directly. We are exciting the structure at one particular frequency, doing the measurement, then going to next frequency, doing the measurement. So this is also a way of acquiring the FRF, or in the frequency domain. So we are directly doing the measurements in the frequency domain. But in the other system, how we are doing is we are basically doing in the time domain and then converting into frequency domain. So here in the EMI technique, we are getting everything in the frequency domain directly. We don't have to carry out any FFT. Alright. So here the piezo materials, they are the key sensors in this technique. So what we do is we visualize the structure as a mechanical system which has some structural impedance Z. So we'll define what is structural impedance in the coming slides. So we visualize that this box is basically representing the structure. So it's an idealization structural impedance, and when we say structural impedance, that means it has inherent the mass, stiffness and damping characteristics of the structure. So everything is inherent inside. So the piezo patch is undergoing vibrations under impulse voltage signal, and it interacts with the structure, and when the interaction happens, then the structure also influences the piezo patch and the current flowing through the circuit. So this electrical circuit which we are showing here, it basically represents the current flowing through the circuit. It represents the essence of the structural parameters: mass, stiffness, damping characteristics. They affect the current flowing through the circuit. So imagine, for example, if the structure is very, very stiff, then the structure will oppose. It will oppose the vibrations of the patch. And if the structure is very, very flexible, then we can expect that it will not be able to oppose or provide the adequate stiffness to the piezo patch. So piezo patch will be vibrating almost freely. So all that is reflected in the current flowing through the circuit. So here now another equivalence I will draw with the what we have discussed for the case of the global vibration techniques. So here the force is applied by the piezo patch. So it's like the mini shaker. So here, because the force is dynamic in nature, we can represent it by a phasor. So the piezo patch is vibrating with angular frequency omega, and we can, just like in the case of the global vibration techniques, we can say that there are two components. The horizontal or the real component is the actual force acting, and the vertical component or the imaginary component is just the imaginary one. So this is the actual force which is acting, say, cosine, and the other is the imaginary component, and then the response that will also lag behind. So here when we say impedance, what response specifically we are targeting? We are targeting velocity response, because that's how we define impedance. We define the mechanical impedance as the ratio of the force to the velocity. Alright, so for example here, because we have applied force, a sinusoidal force, the resulting velocity at this point, that will have some phase difference with the applied force, but the frequency will remain same. So if we find out the ratio of the applied force at that particular point with the resulting velocity at the point, then that is the mechanical impedance of the structure. So this mechanical impedance is a unique function of structure stiffness, damping and mass characteristics. So we'll use this term very often in connection with the EMI technique. So what is mechanical impedance? Mechanical impedance in true sense or in mathematical sense is basically the ratio of the applied force to the resulting velocity at that particular point. Okay, and this we represent just like this box. So we are assuming that the patch is connected at the two ends, and the two ends, they are acting as if they are providing impedance. So impedance on both sides of the patch, and that's how we have this kind of impedance based model of the structure piezo system. So now this equation was derived by a researcher named Liang in the Virginia Tech, and he came for 1D case, that if we are assuming the piezo patch to be 1D structure, just like a rod undergoing vibrations and bonded on a structure, then the electrical admittance will be given by this kind of equation. So we'll go in detail what the various terms of the equation they are suggesting. So basically what you see here, that the dimensions of the patch, they are coming into picture. W, L and H, they are dimensions of the patch. W the width, H the thickness and L the half length of the patch. So these are coming into picture, and after that we have the term omega. So this admittance is for one half of the patch, and if for example we have a patch like this, in this configuration we will have to use a factor of 2 also, because both the parts are contributing. So epsilon 33, this is the electrical permittivity of the piezo patch. Z we have defined, this is the mechanical impedance of the structure, and ZA is the mechanical impedance of the piezo patch. Just like we have defined the mechanical impedance of the structure, we can similarly define the mechanical impedance of the piezo patch also in terms of the force and the resulting velocity. D31 you are all familiar. D31 is called as piezoelectric strain coefficient, and we know how to determine that. Then YE with a bar, this is basically the Young's modulus of elasticity of the piezo patch under a particular condition. And what is that condition? This is under condition of zero electrical field. That's why we have here E here. So it means that this has been measured under constant, that is zero electric field conditions. And similarly, epsilon 33 tau is the electric permittivity. So this is measured under constant stress condition or zero stress condition. Okay. So K is the wave number. So we'll define in the next slide what is wave number. So wave number comes into picture when we basically do the derivation. In the next class, we'll do the derivation of this equation. So K, or to be more exact, this we prefer to use the symbol kappa. So this is the wave number, and wave number is basically given by this equation. Basically, when we solve the differential equation, then this parameter comes into picture, wave number, and this is omega under root rho by the Young's modulus. So we'll derive this, and each and every term will be clear when we derive in the next class, because today's class I just want to introduce this technique to you and some of the case studies. So basically now here the admittance Y, it is an indirect representation of the structure impedance Z, because now what we see here, that in the equation the admittance, whatever is the admittance resulting from this measurement, it's a function of the structure impedance Z. ZA is constant, ZA is for the piezo patch. So if there is any damage, then what parameter will change? Epsilon 33 will not change. Permittivity is a constant property, it will not change. What will change is the mechanical impedance of the structure. So when mechanical impedance of the structure changes, then the measured electrical admittance will also change. So this is used for damage detection. So here the point is that there is no problem, just like in the case of the global vibration techniques. In global vibration techniques, when we are raising the frequency, when we are going to higher modes, we face difficulty. We find that as we are going from mode number 1 to mode number 2 to mode number 3, the difficulty with which, or the effort we have to apply to obtain the mode shape, that also increases. So only we are able to obtain first few modes, maybe first 3 modes, or at the most first 5 modes. Here there is no frequency limitation. Here basically we can externally excite the piezo patch to our desired frequency, and it can go in limits of several thousands of kilohertz. Otherwise, in the case of the global vibration techniques, for example, if we are using shaker has a limitation. You can't go beyond a certain value, and therefore you cannot go beyond say 100 hertz or 200 hertz or something like that. But here in the case of the EMI technique, as long as our LCR meter is having the provision, we can go into the kilohertz range very easily. So how does this identify damage? So we have just seen from the equation that if there is any damage, then there will be definitely change in the stiffness, mass and damping characteristics, and that means the mechanical impedance undergoes change. And when mechanical impedance undergoes change, then this means that there is change in the admittance, and this gives us indication of damage. Or in other words, we can interpret it from the wave propagation, that the patch is undergoing vibrations. So if it's in a surface, that means it's emitting out waves readily away from it, and if there is any damage in terms of crack. So what will happen? It will obstruct the path of the waves, and the waves are very small. So typically the wavelength, the order of the wavelength is in few mm. So if their wavelength is of the order of few mm, then it will be able to detect damage of that order. So in the global vibration techniques, if you find out, for example, the first mode shape or the second mode shape. So second mode shape, what is the wavelength? Wavelength is equal to the length of the structure. So that's why it's not able to get affected. The mode shape does not get affected by very small damage. So if we have the waves which are of higher wavelengths, they would cross a small damage without getting affected. So here the wavelength of the emitted waves is small enough that it gets affected by very small damage, say in the range of few mm. So the cracks, the occurrence of cracks that disrupts wave propagation, and this is reflected in the signature. So how it does is we'll see, but here the point to be noted is that here stress waves of very small wavelength are generated and local structural modes are excited. So this has the advantages. Number one, it has very high sensitivity that we can detect incipient damage, and the other point is that here the sensing zone is localized. Why localized? Because here the as we are increasing the frequency, so the energy tends to get limited to the area surrounding the piezo patch only. For example, if you see the global modes of vibration, so global modes of vibration, the entire structure is affected. In the first mode, second mode, third mode, these modes, the mode shapes, either single trough in the case of the first mode shape, double trough in the case of the second mode shape, that means the entire structure is undergoing vibrations. So waves are these vibrations, they have influence, global influence. But as we are increasing the frequency, then what happens is that it keeps on shrinking. So at one point of time we have only the local modes. So local modes, they are basically limited to the particular region surrounding the patch, and then if there are any joints or any kind of discontinuities, then the waves, they are not able to cross over them. So the zone of influence of the piezo patch gets limited. So that gives us the advantage that we can pinpoint the damage location. So that means if we have an array of piezo patches, then the piezo patches which are near the damage, they will be affected more as compared to the piezo patches which are away from the damage location. So any doubt till now? If you have any doubt till now, just let me know before we go further. Any question, any doubt? So please keep asking while we are doing. So I hope that you are understanding everything. So basically here, as I showed, that we acquire the signature in two components. The real part is called as the conductance and the imaginary part is called the susceptance. Alright, and this equation I am just projecting again. So in fact, what you can do is that you can separate this into two equations. Right now is a equation in the complex form, but you can very easily separate it out if, for example, you expand. If you expand all the complex terms, then you will be able to separate out the equation, the real and the imaginary parts. Now how we interpret damage, that let's say if we have this beam and we have done a small damage, just 5 mm hole is drilled, but then how the signature is affected. So this is the signature in the undamaged state. As long as there is no damage on the structure, we'll always acquire the same signature within the resolution of the instrument we are using. So LCR meter, it has very high resolution. So the change, if you are coming after some time and again acquiring the signature, the change will be very small, within say 0.2%. But then if there is a damage, then the damage gets very easily identified. it will change the signature in a very marked way, and that reflects in the form of change of signature. So we can very easily pinpoint that now damage has occurred using the EMI technique. So if we are using the global vibration technique, we will not be able to see this change in terms of the frequency or the mode shape, but the EMI technique will be very easily able to capture. For example, here just a single hole has been captured very easily. But we had seen in the global vibration technique, the case study where we were drilling the holes, and when we are drilling the holes, state 1, state 2, state 3, there was hardly any change in the frequency. So this is the difference between the global vibration technique and the EMI technique. So EMI technique is very good for identifying the incipient damage, and the global vibration technique, they are very good for identifying and locating damage which is of the global nature. Alright, now the thing is that how do we quantify the damage? So here basically signature is like an FRF, and when there is any change, then what happens is that we see that some of the peaks, they have shifted. So some of the peaks, we will find that they are shifting because of the loss of stiffness, they are shifting to the left, and in the process, because these are highly local modes, some new modes may be created. So we may find that some new peaks have also come which were not there otherwise. So now we'll do a case study. We'll just describe two case studies, first on a concrete block and then on a concrete structure. Once we do that, then we'll cover another case study to highlight the power of the technique to capture very small damage which is not captured even by our naked eye. So if you have any doubt till now, please raise your hand, else we go on the case study. So, today we will cover at least one case study we'll cover, and the remaining we'll cover in the next class. So this case study covers tests on concrete blocks. So this is an old study that was done because prior to this the technique, EMI technique, was being used in the aerospace industry, and this was first time we performed some experiments on concrete tube, and we were also not sure whether the technique would be suitable for the civil structures like concrete or not. So here what you see that we had bonded the piezo patch on a concrete beam and standard concrete on a concrete cube, standard concrete cube used for compression tests, and here this instrumentation was done, and then the cube was loaded in the compression testing machine. So we did not load it in a single go. So what we had done is that we applied the load till a particular load level, and then we brought the cube back to the lab because the impedance analyzer, that time LCR meter was not invented. At that time impedance analyzer term was used, so we were using HP 4192A impedance analyzer. So we were acquiring the measurements in another lab. So first of all, I loaded the cube to 100 kilonewton load, and then the load was released, and after bringing in the lab, we found that there was some change in the signature. So to investigate further, I loaded the cube to 200 kilonewton, and then there was further change. Now you can see that 100 kilonewton and 200 kilonewton, they are bringing about some definite change in the pattern of the signature. So the frequencies, they are shifting leftwards. Now I would like you all to do an exercise. Say this is the standard cube 150 mm size. So if you are applying 100 kilonewton of the load, how much would be the stress? Can anyone calculate this in megapascal?
Sir, what is the cube size?
Standard cube size 150 mm. So for 100 kilonewton, how much will be the stress? So we are interested in, just analyzing this.
4.4 MPa, 4.4 MPa.
4.4 ampere, right?
Hmm.
Now I would request you to calculate the resulting strain also. So how would you calculate the strain?
Strain. Oh,
The stress upon
if we know the grade of concrete, then 5000 root FCK we can calculate the modulus of elasticity. Stress by modulus of elasticity will be strain.
Alright, so I think
That's right.
you can do that if you just assume that the concrete grade is M25 and find out the Young's modulus and then find out how much is the strain.
25,000.
Young modulus will be 25,000 Newton per atom square.
Yeah.
And then if we divide that F by that, that will be the strain.
So 0.000017776.
Okay.
And
Just if you want to tell me in microstrains, just multiply it by 10 to the power 6. How much will it come? In microstrains.
Okay.
Multiplied by
Sir,
10 to the power 6.
177.6.
177
177.6
microns, right?
177 is okay.
Alright, so this
Yes.
is the strain level we are subjected to in compression. So basically at 177 microns, this implies that the cube is undergoing small micro cracks, very small micro cracks. Alright, and when we are doubling it, so it will be 2 times 177. So definitely when the stress level is double, okay, then what will happen is that the cracks, they will further expand, and this is reflected partly in the signature. Alright, finally we then did these series of load applications, and we could see that these signatures are undergoing shifts. So from 0 to 100 kilonewton to 200 kilonewton and like this. So 100 kilonewton, you are saying that the strain is 177 microns. So this is the strain, so I'm just using the symbol for microns. And what would be the strain at 600 kilonewton? Of course, the Young's modulus change, but assuming that we are doing a hypothetical case, let's say linear, what would be the strain at 600?
600, it will be 6 times.
Yeah, can you tell me the value?
If Young modulus is constant. Okay. 177 into 1062 micron strain at 600. Assuming that the Young modulus is constant.
Yes, so Young's modulus, it also undergoes change as we are, doing the loading. So Young's modulus also change. And this is, now remember, this is like a hysteritic loading. It's not in a single go. We are loading to a particular level and then unloading. Next cycle we are doubling the load and again unloading. So Young's modulus would gradually reduce. So our calculations of the strain, they would not be that accurate, but even if we assume that the Young's modulus remains same, so what value we are getting for 600? Can you tell again?
1062 microstrain.
1062. So 1062 means 1000 microns. Alright.
Yes, sir.
How much is the compressive strength of concrete in terms of strain?
Ultimate 0.003.
In microstrains it will be 3500, right?
3000.
Exactly. So our strain level is quite less than that, right? But of course, this is very crude estimation. Our strain level is much lower than that. But then here the concrete cube is inherently undergoing fatigue, right? Because it's a repeated loading. So it is undergoing fatigue. But till 600 kilonewton externally there was no sign of any damage. Possibly the damage was inside somewhere. Okay, damage was inside somewhere, and we were seeing some changes here in the signature. Now something dramatic happened after 600 kilonewton. So stress etc. we have done the calculations already, strain etc. So we have done this. So now at 700 kilonewton something dramatic happened. Now you can see here the earlier signatures, they were following one trend, and mostly it was lateral shifting. Lateral shifting, something was happening. But then at 700 kilonewton there was a very strong upper higher shift, and then what happened was that at the next very cycle the concrete cube failed. We could not acquire the signature at 800 kilonewton. So this pointed out an impending failure. So till 600 kilonewton there were micro cracks. Definitely, how do we say that there would be micro cracks? From the estimated strains there will be 100% some micro cracks, and there will be a major crack also, maybe inside, but externally it was not visible. But at 700 kilonewton, our sensor, it provided us that something drastic is happening. Okay, so this is what was the first test when we applied the EMI technique on concrete. Okay, so any question on so far?
Sir, is that the change of signature at 700 kilonewton due to this micro cracks become the larger one?
Yes.
Is it the reason?
That is the possible reason, that the cracks, they were accumulating, and then there was a very high level of damage inside, which was still not visible. But then the piezo patch, it identified it. Okay, let's go further. Now how do we quantify damage? Because see, visually we can see the signatures and we can see that the signature is undergoing some change. But then if we want to mathematically quantify damage, then we have to use some mathematical sort of system. For example, root mean square deviation is there. So root mean square deviation, what we do, we find out the difference between the signals. So for example, before damage we have array, a one-dimensional array, and after damage also we have the one-dimensional array, the signature. What we find, point by point, we find their difference, we square it, and then the sum of squares, and we divide it by the sum of squares of the prior damage signatures. So this is called as root mean square deviation. What it does is that it because somewhere there will be positive, somewhere will be negative. The difference will be somewhere positive, somewhere negative. So if we, for example, do algebraic sum, so that will cancel out some of the terms. So that's why this square is used here, root mean square deviation. Then there are other techniques also. They are all mathematical techniques. Statistical, we say statistical techniques like signature assurance criteria, adaptive template matching, waveform chain code, and many other. They are based on some kind of mathematical expression like this. So this is a non-parametric damage quantification. So we applied it in the case of the concrete cube over two frequency ranges, 40 to 65 and 370 to 490. Now you see here the difference. So for the 40 to 65, this is how the trend was there, that it was increasing. Then after some time it became constant and no change, and then something near the penultimate stage. So what is your now comment or any observation on this plot? So what we find is that when the damage is very small, immediately we are seeing some deviation in the signatures, and this is quantifiable. say 10%. So in the case of the global vibration technique, we were not getting this high change in the frequencies. How much we were getting? Says either there was not even a measurable change, or it was 0.5% or something. But here we are getting bit appreciable in quantified term. But of course, the issue is that this is a non-parametric. We cannot relate it structurally, but it's good enough. It's statistical tool. And then what we find that when the damage is progressing further, now perhaps I ask you a question, where could the damage be moderate damage? Like definitely when we are applying 100 kilonewton, it was incipient damage. But where could be moderate damage? So moderate damage is a thing which is subjective, but if we say severe damage, so here at 700 kilonewton there was a severe damage, right? There was something severe damage, and at severe damage we got an indication. But where was the moderate damage? So moderate damage, what we see this zone, we can say that this was the moderate damage. But in the moderate damage, although the signatures they were changing, but then in the root mean square deviation, is there any change? Is there any change in the root mean square deviation? Any appreciable change? The answer is no. It was more or less flat. Right. So just note down this observation that in the incipient damage it showed some very good response, and in the case of the penultimate damage also we could see something. But when the damage was moderate, that time we were not seeing much. But I am sure the damage must be expanding, because our strain levels, they are increasing by the same factor, 177 microns at least. So there must be the damage growth must be there, but we are not able to appreciably see that. All right. So now let's do another case study. This I will do a bit fast, and then the third case study we'll do next time. So this was the next case study. So this was a two-span model of a bridge, a scaled model of a bridge, reinforced concrete bridge. So basically here there were two spans, and it had continuous support in the middle, 5 meter span, 5 meter span, roughly 5 meter span. To be exact, it was 5.175 meters, and we had positioned some piezo sensors here. So that is the support region. So what I am showing here is the one half of the patch, one half of the structure. This span is being shown, the second span, this span is being shown here in large view, and this is the support. So near the support, some piezos they were bonded, and some piezos they were bonded near the midpoint. Alright, so this is the elevation. So now it must be clear from the elevation where these piezo patches they were bonded, and they were bonded. We tried to bond some piezo patches on the bottom side, soffit also, but it was not successful because there was a limited time. So we could not get ready to use piezo patch on the bottom side, the exact place where we have the tension at the midspan. So these are the patches now. So this is the picture of the top view of the slab before loading, and then this loading system was there, and using hydraulic jacks manually the loads were applied on the two spans. So there was a protocol. One span was loaded, then it was unloaded, then the other span was loaded, then both the spans were loaded. Some protocol was there, and just I want to show you how the computational systems of the 90s they look like. So this is Pentium 1 computer, and here we have the impedance analyzer. Now it's very different, very bulky as compared to the compact LCR meter we are using these days. And some of you, I'm not sure whether you have seen these kind of monitors or not. So this is a picture of 1999. So this is how the loading was done. That one panel was loaded to 40 kilonewtons, then unloaded, then the other panel was loaded, then both the panels were loaded. So this way it was done, and in between the signatures were required. For example, here the baseline signature was required. Now at this stage again the signature was required, then both panels were again loaded to 64 kilonewton, and then signatures required, and finally they were loaded to 69 kilonewton, and that was the failure point. So temperature was more or less constant. So there were 3 cycles of the loading. So strains were also measured. So here, for example, the top strain was 189 microns. So now we have some idea that it's the level is similar, because in the case of concrete cube 100 kilonewtons, what was the strain level? 177 microns. So here we are quite close, and at the top, the top fiber strain was in tension and bit high. Now tension strain and compression strain. So if we are talking 189 in compression and we are comparing it with 450 microns in tension, so 450 microns is giving rise to lot of cracks. They are tensile cracks now. So the surface would be full with cracks in the case of the tension, but compression they would not be that visible. And these are the signatures after cycle 1. So what we can see here, the patch 1, we can see some change in signature. Patch 3, there is no change in signature, practically no change in signature. Patch 4 also there is change in signature, but the maximum change we can see in patch number 5. And here we are seeing the root mean square deviation also. So we can very easily see that the root mean square deviation values, they are correlating well with our visual observation, that for patch number 3 there is hardly any value of the root mean square deviation, very small, say less than 2%, and for patch number 5 it's of the order of 25%. And then after cycle 1 we took a picture of the top surface of the slab. Now you can very easily correlate that piezo patch number 5 is showing very high value of the damage index or root mean square deviation, and we could visually also see that in terms of the signature. And what you can observe is that there is a crack very near to the piezo patch number 5. Rather, it was passing through the bottom of the piezo patch, just touching it. So that's why it has shown very high value. And other patches, they did not have patch in the very close vicinity. The cracks were there but a bit away, so we were not seeing anything. And then in the next cycle we find that the piezo patch number 3, which was showing very small value in the next cycle. So after cycle 2 you can see the load versus displacement curve, it has started flattening, and we have high values of these strains also. And then after cycle 3 also we could see that now the structure has more or less failed, and there was some slip. We could see debonding of the strain gauges also. So what we could see then, that the observation was with respect to the patch 3. So patch number 3, earlier it had very small value of the root mean square deviation, and that suddenly increased after cycles 2 and 3. And in fact this correlated very well with the surface. So now what you can see is that a crack has occurred near patch number 3 also. It was not there after cycle 1, but after cycle 3 crack has occurred near patch number 3 also. And also the other cracks, they have widened enough. Okay, so this is the the response, the signature response of patch number 3. So after the first cycle there was hardly any change in signature, but after the cycle 2 and cycle 3 there was appreciable change in the signature. Now another point is that there was hardly any change in these signatures of these patches 9, 10, 11. So if we see, there is hardly any change. The reason is that they were in the compression zone. So compression zone, there were micro cracks, but not they could not mature into high greater or wider cracks. So there was some change, but the values of the root mean square deviation, they were very small. So why this reason? The reason is that they were in the compression, so cracks they widen up much later, just like in the case of the concrete cube. Concrete cube, we could see that in the moderate stage, the the root mean square deviation, that was more or less flat. So that phenomena we could see here, because in the case of the cube we had subjected it to only compression, but here we have flexure, so we have bonded patches near the tension zone and we have also bonded near the compression zone. So the findings could be summarized that the EMI technique, which was so far employed on smaller space structures, it is suitable for RC structures also. Let me just change the spelling, just give me a minute. Some spelling error I just noticed, so let me just change, and this would be the last slide for today. So basically this was the first study, both the cube and the beam, RC beam, but this study, it gave credibility that the EMI technique can be extended to concrete structures also. Otherwise there were doubts whether the technique would work for concrete or not, because concrete is a very non-homogeneous material, then it has very high level of damping as compared to the other structure types. So this study highlighted that the EMI technique can work on the RC structures also. And signatures, they are sensitive to cracks. So when we have the micro cracks, definitely we will pick them up, and in certain cases when the structure is about to fail, that time also we will be able to pick up. Another point was that the piezo patches, they have relatively small zone of influence for crack detection. This one can see that this is a shortcoming, but it's also an advantage because it helps in damage localization, because we can use an array of patches very effectively. For example, the way we have used in the case of the RC bridge. So what we have done is we have employed the array of the piezo patches and we can very easily use it. So this is very much suitable for damage localization. So I think I'm ending the lecture here. So if you have any doubt, just you can raise your hand, or any discussion, any comment, you can raise your hand. So basically the main objective of today's lecture is that you understand the working principle of the EMI technique. At least one person when makes beginning, then others also ask. Yes, Aniket, you ask some question.
Sir, when we calculate using piezo patch, when we calculate the impedance, that means Z. Z means structural impedance. We can calculate. We have to calculate from there. How can we calculate ZA? That's mean impedance for piezo patch. What is the procedure?
Okay. Yes, this part will be doing in the coming lecture. So this lecture, we have not focused on the computation part, we have focused on the measurement part only. So what we are doing is we are showing you how the measurement is made, and we are making the measurement of electrical admittance. So what we are obtaining is electrical admittance, and when we are doing root mean square deviation, we are doing with the electrical quantity directly. But yes, you are right in your intuition is absolutely right. We can use this equation derived by Liang to obtain the mechanical impedance of the structure. It's called as drive point mechanical impedance. So that computational procedure will be learning in the forthcoming lectures. All right. And then the other question is, how do we calculate the mechanical impedance of the piezo patch? I give you a hint. How do we define mechanical impedance? We define mechanical impedance as the ratio of the force to velocity. So all you have to do is apply force and at that point measure velocity. But how do we measure velocity? Velocity measurement is difficult. So in place of velocity, we can measure displacement. And what is velocity?
Okay, sir.
Velocity is just the time derivative of displacement. So whatever
Okay.
displacement amplitude you have obtained, you multiply it by omega, you will get velocity. Okay. So we
Okay,
have
sir.
the applied force, we have the measured velocity. The ratio will give you the mechanical impedance of the piezo patch.
Okay, sir.
Alright.
Okay, sir.
Any other question? So if no question, I invite Dr. Dhawan. So he was saying that we are planning two things. One is the site visit to Signature Bridge. That Dr. Dhawan will talk with the concerned person, the engineer in charge. But he said that we can also plan a test on some smaller structure, some say foot over bridge. So he wants some volunteer who can just talk with the concerned executive engineer, or he get the contact information of the concerned executive engineer, and then Dr. Dhawan will talk with him to get the required permissions.